Hello students, welcome back to the revision class of the chapter Light Reflection and Refraction. In this part, we will begin with the topic formation of images by a convex mirror, and also we draw the ray diagrams for the image formation by the convex mirrors. And in the previous part, we saw the properties of images formed by a concave mirror, and we have seen that how the properties of the images change with respect to the position of the object. Similarly, in the case of a convex mirror, there are only two situations. One, when the object it is at infinity, and second one is when the object placed at some finite distance. In each case, we get a different kind of image. So let us say in the first case, when the object is at infinity, the image formed is almost point sized and appears at the focal point of the convex mirror, that is behind the mirror. Since the image is virtual, it cannot be projected onto a screen. For example, if we hold a pencil far away from the convex mirror, its image appears much smaller at the principal focus, and that is virtual and erect. And in the second case, that is when the object is placed at some finite distance, the image forms between the pole and the principal focus of the convex mirror. And here also, the image is virtual, erect and smaller in size, that is diminished. These are the only two situations that we encounter in the case of a convex mirror. And next we will draw the ray diagram for both the cases to understand them visually. We take a convex mirror and we mark the pole and center of curvature of the convex mirror, and the line joining these 2 points is called the principal axis. Now we take a beam of parallel rays that are incident onto the reflecting surface of the convex mirror, and after reflection they diverge in different directions, and if we extend all the rays that are diverged in the backward direction, they will meet at a point on the principal axis, and that is the principal focus of the convex mirror. In this case, the object is at infinity and its image is formed at the principal focus of the convex mirror, that is behind the mirror. Now we note down these observations, that is when the object is at infinity, the image is formed at the principal focus of the convex mirror and the image is virtual, erect and highly diminished. And we go for the second situation where the object is placed at some finite distance and we take two rays that are coming from the object. Okay, one is the parallel and the second ray is incident obliquely on the reflecting surface of the convex mirror. And these two rays, okay, after reflection, they go in different directions. We are taking such a rays that after reflection, okay, they go in a different ways, such that when you extend them in the backward direction, one appeared to coming from the principal focus, the other appeared to coming from the center of curvature of the convex mirror. And the intersection of these two lines, it gives the image point of the object. Therefore, the image is formed in between the principal focus and the pole of the convex mirror, that is here. And this image is virtual because it is formed behind the mirror, erect, and it is smaller when compared to the size of the object. Therefore, it is diminished image. Now, the observations are the object position is at some finite distance and the image is formed between P and F. And the image formed is virtual, erect and diminished. Applications of convex mirrors. Two important features of convex mirrors. One is, since they are curved outward, they provide a wider field of view. And second one, they always produce a virtual, erect and diminished image of the objects. Because of these properties, convex mirrors are used in various places. The first one is, I think you might have seen, every vehicle is fitted with a mirror, that is a convex mirror. That means the convex mirrors are used as rear view mirrors in vehicles so that the driver can see a larger area behind and drive safely. They are also used in parking areas and shopping malls as they help people see around corners or wide halls, reducing the chances of accidents and ensuring safe movement of vehicles and pedestrians. Next topic is new Cartesian sign convention of spherical mirrors. So while calculating image distances and determining the nature of images, we may face many difficulties. To avoid these, to maintain uniformity and consistency, we use Cartesian sign conventions, which helps prevent errors and confusion in calculations. And these conventions are very simple to understand. Take a concave mirror or a convex mirror and then mark the pole, and the horizontal line passing through the pole is the x-axis, and say it is x dash. And the first convention is all the distances are measured from the pole. This is very, very important. So whatever the distance that you measure on the horizontal direction, you have to start always from the pole of the mirror. For example, if you are measuring the object distance and if the object is placed at the left hand side of the mirror, then you are measuring from the pole to the object. and if the image is formed on the right hand side, then it must be measured from the pole to the right side. Whatever the distance you measure, you have to start from the pole and then you have to go to the image or the object. And if you are measuring the radius of curvature, even further also you have to start from the pole and then go to the center of the sphere. And if you are measuring the focal length, even then also you have to start from the pole and go to the focal point. For the second convention, you take an object O which is placed in front of the concave mirror, and the light which is coming from the object, it travels towards the right side and incident on the reflecting surface of the concave mirror. Therefore, this light is the incident light and the direction of the incident light is towards right side. And there are two types of images possible for the given object. So the image can be a real one that is formed on the left side of the mirror, or it can be a virtual one that is formed behind the mirror. Now the second convention is that distances measured in the same direction of the incident ray are taken as positive. Next convention, distances measured in the direction opposite to the incident ray are taken as negative. For example, if you are measuring the object distance, you need to start from the pole and you have to go to the object. So this is the object distance, and object distance, it is denoted by u. So when you are measuring the object distance, you are moving opposite to the direction of the incident light. Therefore, it is taken as negative. And if the real image is formed, then the image distance is also measured from the pole. Therefore, even in this case, you are moving towards the left side direction, that is opposite to the direction of the incident light. Therefore, the image distance, it is denoted by v, and it is also negative. And if the image formed is a virtual one that is formed behind the mirror, for this image, the image distance is measured while moving towards the right side. Therefore, that is in the direction of the incident light, and the image distance is taken as positive. The next one, perpendicular distances above the principal axis are taken positive and perpendicular distances below the principal axis are negative. That means if you are measuring the height of the object, that is you are measuring in the upward direction above the principal axis, therefore they are taken as positive. And if the image is formed a real and inverted one, you need to measure the height in the downward direction, that is below the principal axis, and they are taken as negative. To note, for concave mirror, the focal length and the radius of curvature are negative because while measuring the focal length and the radius of curvature, you have to start from the pole and you need to move in the direction opposite to the direction of the incident light. Therefore, they are taken negative. And for convex mirrors, the focal length and radius of curvature are positive because you are moving in the direction of the incident light while measuring this focal length and the radius of curvature. Mirror formula and magnification. So mirror formula, it is a relationship between object distance, image distance and the focal length of the given spherical mirror, and it is given by 1 by f is equal to 1 by u plus 1 by v, and we must use the new Cartesian sign convention while substituting the numerical values for the object distance u and the image distance v, focal length f and the radius of curvature r, while using the mirror formula in solving the problems. That means these values are positive when you are measuring in the direction of the incident light, or they are negative when you are measuring these values in the direction opposite to the incident light. Next one is the magnification. The magnification produced by a spherical mirror shows how much larger or smaller the image is compared to the actual object, and it is given by the magnification m is equal to height of the image by height of the object, and it can also be obtained in terms of the object distance and the image distance. That is, the magnification m is equal to the height of the image, that is h dash, divided by the height of the object, that is h, and it is also obtained in terms of u and v, that is minus v by u. And here the height of the object is positive because the object is usually placed above the principal axis. We measure above the principal axis in the vertical upward direction. And the height of the image is positive for virtual images because the virtual image formed either in the case of a concave mirror or in the case of a convex mirror, it is always erect one, and the height of the image is positive for virtual images, and the height of the image is negative for real images because the real image is always inverted one, and the negative magnification indicates the image formed is the real image, and a positive magnification indicates the image formed is a virtual image. With this, all the concepts of the part reflection of light are completed. Thank you for watching the video.